Hello, colleagues. My name is Yuri Petrov. I am from St. Petersburg State University. And first of all, I want to thank all of the participants of our mini symposium for their valuable contributions. I hope all of you and your families are well and healthy. And I also hope, my friends, soon we would be able to get together again in joining personal meetings. I'm going to talk about dynamic fracture mechanics with respect to its relation to crack propagation problem. This is a couple of well-known pictures demonstrating crucial importance of crack propagation modeling. And this is a brief outline of my talk. My starting point is the classic fracture mechanics. State of the problem arises from classic principle associated with strength and fracture toughness. It corresponds to the basic idea of the energy balance, so that we must have the required amount of energy released per unit of a new surface to produce fracture at the crack tip. And the specific energy ought to be material property. The main result of the elastodynamic analysis of the problem is that the stress field in the vicinity of the crack tip is a square root singular, similar to the quasi-static situation, and the singular part of the near tip stress field can be written in this form. The amplitude of the singularity is then characterized by the single parameter kg, called the dynamic stress intensity factor. And here it is mode 1 considered. I will talk only about this case of mode 1. And the K1D is a function of time and the crack speed. Applying Griffith's energy balance and the elastodynamic solution, we complete the dynamic fracture problem and provide the crack tip equation of motion. Here, gamma to the right part is the fracture surface energy and is a material property to be determined experimentally. Just note that gamma may also depend on the crack tip position and the speed, so it is very, very complicated functional that is proclaimed to be a material function. In terms of the stress intensity factor, we can formulate the same principles in forms of the following equations, where the right parts ought to be considered again as material properties. And there are two basic consequences from this classic analysis. First, it predicts that the maximum speed which is possible for a crack is the Rayleigh surface wave speed. Second, it indicates that there is a unique relation between the crack driving force characterized by the stress intensity factor Kd and the crack speed V. So there should be a unique Kv relation, which is normally considered and ought to be taken from experiments and then incorporated into theoretical modeling or in numerical calculations. We think that it should be done this way, but actually it is not the case. So why it is a problem? It is a problem because it turned out that many experimental observations of brittle fracture contradict both of these predictions. Nowadays, there exists a big deal of confusion in the interpretation of experiments on propagating cracks. And here I conditionally specify just only three main wide viewpoints related to 3 types of classical tests. First, on the left side, some of the scientists, like for instance Irwin and Berry, definitely support the existence of a unique KV relation. Using dynamic photoelasticity experiments and high-speed filming of propagating cracks in some materials like Homalite 100, they have provided data in support of that relation. And so this is the KV relation, like this one. But the second class of experiments, it's in the middle of this slide, and there shows that there are some other experimental observations, like those by Professor Jörg Karthoff, which are questioning this principle. Here we have similar KV curves, but we have to note that it is not a unique KV relation, because Karthoff results show that its dependence on specimen, it shows its dependence on specimen type, in particular on specimen geometry. So it seems that it is not a material relation. So it's important here that both types of experiments, just on the left side and in the middle, all these cases are specified by slow static loads applied to the sample prior to the initiation and then further acceleration of the crack. So this is a dynamic which appears slowly from the static situation. When we have a sample which is loaded statically, and then we accelerate the crack, providing the dynamics to our experiments. And so let's come to the third case, and this is on the right side. And so Ravich and Arendt-Knaus, for instance, employed the method of caustics with Homalite 100, the same material, and the loading of the crack was extremely dynamic, and it was produced by electromagnetic impact for the duration of 100 microseconds during the experiment, and then utilized large plates to imitate the unbounded medium, so that the problem was typically dynamic, and they just got straight lines here. Just to compare, this is denoted the same curve from the left side, but actually they just observed these straight lines. The result indicates that the lack of one-to-one relationship between K1 and V. So according to them, there is no such relation at all. So these experiments showed that the relation just doesn't exist. And there are many heated debates among all of these people, and all of the arguments concern the correctness of experimental methods and techniques used for registration of past fracture and interpretation of data. But now I'm going to show how this instability can be interpreted in frameworks of special approach based on the spatio-temporal discreteness of the process. My explanation is referred to the incubation time approach and mechanics of continuum. And in the case of brittle fracture, it results in the following fracture criterion. It utilizes two material parameters, d and tau. Material linear size d, it is the size of representative volume for the given scale level, and material time, characteristic time tau, we call it incubation time. In many cases, it represents characteristic time of relaxation that accompanies the process of microcracking that includes microcracking, nucleation, growth, coalescence, preparatory processes that precede the macrofracture event. Eventually, it looks like actually like quantizing the process in space and time, so that we should the special spatio-temporal cell to be considered in this case, and then the critical structural momentum should be utilized, which works within this spatio-temporal cell. So it looks like a quantized approach. Now, how it works, and there is a first example. This is the first example. Consider just the mode 1 semi-infinite crack that is loaded on its faces by the impact pressure, like in this picture. If we solve a last dynamic problem, boundary problem, and utilize then incubation time coupled with this dynamic solution, then we can get some very interesting effects. You can get the effect of unstable behavior of K1D at the start of crack growth. The principal nature of such instability is related to the difference between high rate and short pulse loading. So high rate loading and short pulse loading are principally different. Why? I just try to explain. Suppose that the load on the crack faces, this kind of load on the crack faces, this is just a pressure on the crack faces, acts up to the moment of fracture. And T star is a moment of fracture. In this case, we have a fracture that occurs on the increasing stage of the stress intensity factor, shown here. And let us now fix this particular value of T star. And now I will consider this value as a pulse duration. So I will have this pulse duration, it's noted as number two, in which this T star is just T duration of this pulse. And so we now I consider a short pulse with duration T equal T star, and this pulse causes the fracture event, which happens right at the end point of the loading period, in this case. And now I want just to decrease the amplitude. And my question to you is, will the fracture event still occur if I decrease this amplitude from the case 2 to case 1? The answer is yes, and we still will have a fracture. The answer is yes, and this way, step by step, we can come to a threshold amplitude, and the threshold pulse will produce fracture that occurs on the decreasing stage of the stress intensity factor, like shown in this on this picture. And so a pronounced phenomenon of delayed fracture in this case would be observed. It corresponds to short pulse fracture mechanics, and it leads to a simple explanation of K1D instability, shown here. In this threshold case, the value of K1D will be different compared to the previous high rate loading, when we kept our pressure acting up to the moment of fracture. And now we get an essential scatter of K1D from the lower boundary of this yellow region to the upper boundary. The lower boundary corresponds to short pulse fracture mechanics. The upper boundary corresponds to high rate loading. And this yellow region gives us understanding of the possible values of dynamic fracture toughness that corresponds both with experiments on high rate loading and short pulse tests. But in the case of short pulse tests, we will have this delayed fracture phenomenon. So this theory can be considered just as a dynamic generalization of linear fracture mechanics. Particular materials calculated by this way give good corroboration with experiments. See just examples. Just examples, the K1D for Homalite 100 and K1D for aircraft alloy. So everywhere we can analytically calculate this rate effect and properly evaluate our material parameters. And now let's turn to crack propagation problem. This is a mathematical problem statement here, and then some details of finite element techniques, simulation technique. There is a node release method, special node release method, in which we incorporated incubation time criterion. And let's validate our approach for some well-known schemes, experimental schemes. There are, first of all, the schemes. I want to show the schemes by Fineberg and Dar. They're differing in the way and speed of loading. The slow loading on the way, on the left, and fast impact loading on the right. In both cases, we've got rather acceptable consent with the crack length trajectory, like it's shown here. But what about KV relation here? Let's first let's consider one more scheme. It is here, and this is a dependence of crack length, dependence in time for the scheme of Dar and Knaus. So let's consider one more scheme, and it is a Kalthoff test, but we used a simplified version of these samples subjected to the slow loading realized in these tests. And this is a Dar case. We used modeling extreme impact loading. Our result for the impact case is shown here. What we see are straight lines, discrete values of crack velocity, and big scatter for stress intensity factors. Looks very similar to what was observed in experiments. So let's go back to Kalthoff experiments. Not very bad coincidence between experimental points and our calculations, but we got two KV relations for the same material. But the fitting here was applied to get continuous curves. What I mean, I will explain it a bit later. And here are just experiments of our lab, where crack propagation was initiated by an extreme concentrated explosion of electric wires. We got rather good corroboration between theoretical calculations and experimental functions for the crack length, and very, very unstable values for the crack velocity. But we found that all the instability is covered well by discrete jumps following from theoretical modeling. So just in this range. Now let's come back to slow loading and to what I meant under fitting in the case of Kalthoff's experiments. I meant that even in the case of slow loading, there is a discreteness in V and scatter in stress intensity factor. But if we take here mean values, I can provide a fitting that leads to rather acceptable continuous curves. And so this fitting was applied here just to get this continuous curves. So actually we have this picture. But in the case of extreme loading, impact loading, the fitting has no sense. So we have to take it as it is. On this slide here you see both versions of the behavior. In the upper part of the slide is a slow loading case, just an acceleration from the static. Here KV relation can be fitted due to small scattering. And you can get just an acceptable continuous curve. But below is an extreme shocking loading of the sample. And here, what we see here, the KV relation fades. And so conclusion, all discussed version of dynamic instability, the K1D variety observed for the same material, and the KV relation existence and fading are just essential traits of the spatio-temporal nature and principal discreteness of the fracture process, which can be accounted for by the described approach. So, thank you very much.